Hello, welcome to another module in this massive open online course. So, we are looking at problems in the Fourier transform and specifically the unit step response of the serial RC circuit. All right. So, we have example problems in the Fourier for the Fourier transform, and we are looking at the unit response of the RC circuit. Unit step response of the RC circuit. Okay. And what we have seen is the unit step response is given as the output is yt equals, if you remember, yt equals ut into 1 minus e raised to minus t over RC. This is the unit step response. Okay. Now, you can see the final value, that is, if you look at y at t equal to infinity or t tends to infinity, let us say, we can call that y of infinity equals, well, as t tends to infinity, e raised to minus t over RC, that tends to 0. So, as t tends to infinity, the final output is 1, all right. So, all the voltage will be across the capacitor. Okay. So, y infinity equals 1. Okay. Now, if you look at the initial value, now y 0, that is also fairly clear, y 0 equals, well, u of 0 which is 1, or that is basically u of 0 which is 1 into 1 minus e raised to minus t over RC, that is 1. So, this is 0. So, it starts from 0 and rises to 1, that is what we have seen. Now, final value is 1. So, this is the final value y infinity, this is final value is 1. Now, remember we define the rise time as the time taken by the RC circuit or the capacitor voltage to go from 90% of the final value to go from 10% of the final value to 90% of its final value. Now, 10% of its final value, that is 10% of 1, that is 0.1 into 1 y infinity equals 0.1. Now, what is the time? We have 1 minus e raised to minus, let us call this as your T10, that is time taken for 10% of the final value. 1 minus e raised to minus T10 over RC is 0.1, implies e raised to minus T10 over RC equals 1 minus 0.1, that is 0.9, implies your T10 equals minus RC log natural of 0.9. So, this is your time taken for 10% of the final value. Okay. %of final value. Now, time taken for 90% of the final value, .9 into 1, that is 0.9, Okay. Now, time taken for 90% of the final value, let us call that as T 90, 1 minus e raised to minus T 90 by R c equals 0.9. Now, this implies that e raised to minus T 90 over R c equals 0.1, which implies T 90 equals minus R c ln or log natural of 0.1. Okay. So, we have, so this is basically your time taken to reach 90%. So, this T 90 is basically time taken to reach 90% of the final value. Okay. So, this is basically so this is the time taken to reach 90% of the final value, and therefore, the rise time is basically time taken to reach 90% of the final value from 10%. So, that is basically your T 90 minus T 10, which is basically minus R c log natural 0.1 plus R c log natural 0.9, which is basically R c log natural of 0.9 divided by 0.1. The log natural is the log to the base e. Okay. R c log of 9. So, this is your T rise, which is R c log 9, which is basically 2.1972 into R c. So, this is the expression for the rise time. So, this is the rise time of R c, that is 2.1972 R c or log 9, that is log natural log 9 to the base e times R c. This is the rise time, all right, and you can clearly see as R c is increasing, basically the time constant is increasing, basically the rise time is also increasing. Okay. So, no surprise there. So, as, and you can note that as R c is increasing, rise time is also increasing. As R c increases, the rise time increases. Okay. Now, observe that now we want to relate rise time to the 3 dB bandwidth. Okay. Okay. So, relate the rise time to the 3 dB bandwidth. Now, observe that the response of the RC circuit, and this is what we have already seen, the transfer function is 1 over 1 plus j omega RC. This is the transfer function of the RC circuit, which is basically, you can see this is basically 1 over, well, you can write this as 1 plus j omega over 1 plus j omega over omega naught, where omega naught, now if you recall, omega naught equals 1 over R c. Now, this is termed as the 3 dB bandwidth. Now, you might also remember that this is equal to the 3 dB bandwidth, because h of omega naught, h, that is a transfer function, is 1 over 1 plus j, which implies magnitude of h of omega naught is 1 over square root of 2, correct. and therefore magnitude h of omega naught square equals half. Therefore, the power that is transferred, the output power is half corresponding to that frequency, alright, which basically corresponds to a 3 dB suppression in the power of the signal that is input to this RC filter. Okay. So, the output power is subdued or suppressed by a factor of half. So, output power correct. So, magnitude h naught omega square is which corresponds to, which is equal to a minus 3 dB reduction in power, and hence therefore omega naught equals 1 by RC equals the 3 dB bandwidth. Okay. And now that gives us an interesting relation. So, we have, remember, rise time equals the rise time equals we have just seen that 2.1972 times RC, and 3 dB bandwidth omega 3 dB equals 1 over RC implies the 3 dB frequency equals omega 3 dB by 2 pi, which is equal to 1 over 2 pi RC, which implies your RC equals 1 over 2 pi times the 3 dB frequency. Now, what the only thing that is remaining is basically if you call this, let us say 2, and you call this, let us say 1, now all that is remaining is substituting this value of RC. So, substituting RC from 2 in 1, this gives us the result that T rise equals 2.1972 times RC, but RC is 1 over 2 pi f of 3 dB. The 3 dB frequency implies the rise time is 2.1972 over 2 pi, that is basically 0.35 over the 3 dB. Okay. So, basically that gives us the relation that rise time is so rise time is 0.35 over the 3 dB frequency of the RC filter, which is very interesting. What this tells us is that the rise time is inversely proportional to the 3 dB frequency, which means if the 3 dB frequency is large, right, the filter has a large bandwidth, correct, the rise time is much smaller. On the other hand, if the 3 dB frequency is small, that is, the filter has a very small bandwidth, the rise time is much larger. Okay. So, what this tells us is the rise time is basically inversely proportional to 1 over 3 dB frequency. Okay. So, rise time is inversely proportional. Let us also note that the rise time is inversely proportional to the 3 dB frequency, which is a very interesting relation. So, basically this problem illustrates the concept of this 3 dB frequency, how to derive the concept of rise time, how to derive the rise time, alright, and finally its relation to the 3 dB frequency of the RC circuit. Alright. Let us now look at another very important aspect, one of the one other very important application and another very important concept of the Fourier transform, which is known as the sampling, which is related to the sampling of a continuous time analog signal. Okay. So, let us talk about, now let us come to yet another important concept, that is the concept of sampling. Okay. So, this is, let us treat this as problem number 18, and this is, although it is an example problem, this is a very important concept by itself. This is sampling of continuous signal. Now, consider a signal, a continuous time signal, which looks something like this. Okay. And now, this is a continuous time signal. Okay. This is t, this is a continuous time signal. This is a continuous time signal. Now, before converting it to a digital signal, we would like to convert it into a discrete time signal. So, to convert this continuous time signal into a discrete time signal, we have to look at the values of the signal at discrete time instants, or we have to extract the values of the signal values at discrete time instants, which are regularly spaced. This process is termed as sampling, that is converting this continuous time analog signal into a discrete time signal. This is termed as sampling. So, we place different time instants, okay, at which we extract the values of the. So, let us say this is 0, this is Ts, this is 2 Ts, 3 Ts, minus Ts, and so on. So, these are the discrete time instants. Okay. So, these are the various equispaced discrete time instants, and these are the samples and extracting the samples of the signal at these discrete time instants. All right, this process, correct, is termed as sampling. Okay. So, sampling is a very interesting concept and one of the most fundamental concepts, which has a very interesting theoretical framework, which is basically analog to, or continuous time, that is Ct to dt, that is continuous time. This is what sampling does. You have a continuous time signal, convert it into a discrete time signal by extracting samples at equispaced instants or equispaced intervals of time, and this interval of time, which is of duration Ts. So, you are extracting samples at 0, Ts, twice Ts, and minus Ts, minus 2. So, you are extracting samples at multiples of Ts. This quantity Ts is known as the sampling interval. Okay. So, this is the sampling duration Ts. This quantity Ts is termed as a sampling interval, okay. And this is the first step. So, sampling is basically to convert, that is first step, conversion of analog to 4 analog to digital. Eventually, to convert this analog signal into a digital signal, sampling is the first step, and it is therefore one of the most important steps, because frequently the natural signals are analog, and to store and transmit signals we convert them into digital signals, all right, which is the most popular technology both for storage and communication. So, sampling plays a key role in that, and it is very important to understand the concepts, various concepts and the various aspects of sampling in good detail. Okay. Now, if you look at the sampling, now this Ts, as we said, is a sampling interval. Now, this quantity omega s equals 2 pi over Ts, you can call this as a sampling frequency, or basically the angular frequency of sampling. So, this is equal to sampling frequency. This is the angular sampling frequency. To me, the sampling frequency can also be denoted by Fs equals 1 over Ts. Okay. So, one is the frequency, the other is the angular frequency, all right, 2 pi over Ts, 1 over Ts, all right, the frequency with which samples are being taken for this continuous time signal. Okay. And now there are various techniques of sampling. One of the most simplest methods of sampling is basically have an impulse scaled by the value of the signal at each multiple of Ts. That is, basically what you do is you have impulses which are periodically spaced or equispaced at Ts, at multiples of Ts, and you scale the amplitude, or you scale each impulse by the value of the signal at that particular point. This is known as impulse train sampling. In other words, you have this impulse train of impulses, right, which are of unit scaling, and you multiply it with the signal. Okay. So, what you have is, one of the most popular techniques for sampling is what is known as impulse train. So, this is one of the most popular technique. One of the most popular technique for sampling is impulse train sampling. Now, the impulse train is basically you can write this as summation k equals minus infinity to infinity delta T minus KTS, that is delta T minus KTS, that is impulses of unit scaling at each multiple of Ts. Unit impulses at each multiple of Ts. Okay. So, this is basically termed as your impulse train. So, what you have is you have the time axis, and at each multiple of Ts you have unit impulses. Okay. So, this is at 0, Ts, twice Ts, minus Ts. So, this is basically your impulse train or your train of impulses. Okay. So, this is your impulse train, that is impulses spaced at equal intervals on the time axis at multiples of Ts, where Ts is a sampling interval. Okay. And this is your delta TST. Okay, this is your impulse train. Now, what we are doing is we have our continuous time signal. So, impulse train sampling is simply you take the continuous time signal xt, this is your CT signal, and you multiply it with the impulse train This is termed as your impulse train sampling. This is your impulse train sampling, which is basically, now if you look at this, this is x of t summation k equal to minus infinity to infinity delta t minus k T s. Which is equal to summation k equals minus infinity to infinity x of t into delta t minus k T s. And now you can see delta t minus k T s multiplied by x t, the property of the impulse function basically extracts the value of the signal at the sampling instant, corresponding sampling instant, that is k T s. Okay. So, for instance, they use the property that x t multiplied by delta t minus t naught is equal to essentially x t naught into delta t minus t naught. There is the impulse based at t naught when multiplied by x t extracts the sample, extracts the value of x t at that value t naught. Okay. So, this is equal to your k equals minus infinity to infinity x of k T s delta t minus k T s, and this you can denote this as the sampled signal. Okay. So, this is basically your x of this is basically your so this is basically the sampled signal. Okay. And this is basically, you can see the sample value of the signal at sampling instant k T s, sample value. This is the sample value of the signal at the sampling instant k T s. Now, what we want to do is basically we want to study this sampling process in detail, and a very interesting viewpoint or a very and a lot of insights about the sampling process can be gained by looking at the Fourier transform as what happens to the spectrum of the signal that is sampled. So, what we want to do to understand this process better is to look at the spectrum we want to look at the spectrum of the sampled signal. That is, if we want to ask the question if x t has the spectrum, correct, if x t has the spectrum x of omega, then what is the spectrum of this quantity x t s, that is the sampled signal. What is the spectrum of the sampled signal? That is the question that we would like to address. Now, so we would like to find the spectrum of the resulting sampled signal. To do that, first let us start with the spectrum of the impulse train. Okay. So, you know the impulse train, now if you take a look at this, impulse train equals summation k equals minus infinity to infinity unit impulse functions at each multiple of T s, each integer multiple of T s. Now, you can see this is a periodic signal. This is a periodic signal and the period is nothing but T s. The period is basically T s, and you can see that this is basically, if you look at minus T s, if you look at this here, you will see that this is basically a periodic signal. So, you have one impulse in every interval of T s at every duration of, after every duration of T s, alright. So, an impulse at 0 T s, 2 T s, minus 2 T s, so on. So, this is periodic, and the time period, fundamental time period is basically Ts, and in fact the fundamental frequency of this is 1 over Ts, the fundamental angular frequency is 2 pi over Ts. Okay. So, that is the first thing that we note. Okay. So, this is periodic, period is Ts, fundamental frequency equals 2 pi over Ts, which is equal to omega s. Okay. Now, therefore, this has a complex exponential Fourier series because it is a periodic signal. Therefore, we can develop or derive the CEFS, that is the complex exponential Fourier series. That is, I can express this as delta Ts of t equals summation k equals minus infinity to infinity Ck e raised to j 2 pi k, or e raised to j, simply e raised to j k omega s t, where omega s is the fundamental frequency. That is basically a linear combination, there is a combination of an infinite number of basically sinusoids, harmonics corresponding to the fundamental frequency omega s, and multiples of the fundamental frequency, that is harmonics, right, harmonics at multiples of the fundamental frequency, that is k omega s. Okay. And we can derive these coefficients of the CEFS, the complex exponential Fourier series Ck, and from that we can basically one can derive what is the resulting spectrum of the sample signal. Alright. So, we will stop this module here and continue in the subsequent module. Thank you very much.